Brian, Mike. Thank you so much for the introduction. I just wanted to tell everybody how excited I am to be here. I know formnext is one of my favorite conferences of the year, and although this is a pretty dramatically different formnext than I'm used to, I think it's great to have the opportunity to present some of the things that we've been working on here at Velo. And while I'd love to be in Frankfurt drinking delicious German beer with everybody, I'm happy as a second choice to be presenting here from California, where it's not so bad either. Today, our presentation is going to go over, as Mike mentioned, the new system that we launched a few weeks ago, and how that will pretty dramatically impact costs as they are associated with metal additive manufacturing. So I'm going to go ahead and jump right into this. One of the things that's true in almost everything that's done is that there are trade-offs to be made. And one of the trade-offs that we run across quite frequently in product development and manufacturing is the trade-off between faster, better, and cheaper. And there's a saying where you can have something faster, better, and cheaper, but you only get to choose two. In metal additive, I think that the main focus has been on faster. And this is really, this goes back to kind of the rapid prototyping legacy of metal additive manufacturing and additive manufacturing in general, where the goal was really to get something much more quickly, hence the rapid prototyping. And this has been true for, the last 20 to 30 years across AM. One of the things that Velo was really focused on when we started making our products was the better aspect. And so our goal was really to take metal additive manufacturing and allow for expansion in the better category. And this meant expanding the geometries that could be printed and really expanding the amount of confidence that an end user had in the quality of the printed part. And I think, together we're starting to make that choose two of these a true statement. Whereas in the past, I think that additive manufacturing and metal additive specifically has really been you can have any of these, choose one type of situation. But where we want to be is really kind of the nexus of all three. And this is really where the productionized solution becomes real. It's when you can not only have something faster and better, but you can also start to drive the cost down quite a bit as well. And this is really what's necessary in order to pull a lot of these potential applications into serial production in metal additive manufacturing. So this is what we see as really the next chapter in additive manufacturing. And I think I want to point out that this graphic is slightly misleading in that overlap between those three looks like a small overlap. And that's because it's kind of a difficult thing to achieve. But that doesn't mean that the opportunity is small. On the contrary, the opportunity, if you're able to realize all three of those, is tremendous. And that's really where we'll start to see the technology leveraged across a number of different applications and really start to accelerate that growth and pour some fuel on the fire. So when you talk about production solutions, Velo is really approaching this with one thing in mind going forward, which is going big. And with this in mind, we've developed our new hardware, our new Sapphire printer, which we call the Sapphire XC. XC stands for extra capacity. We wanted to keep it simple. The system is designed for faster printing and dramatically reduced part cost at the end of the day. So the system as it is right now is a 600mm diameter build platform with a 550mm Z height. It's a pretty large machine. And with this, we're achieving up to 5 times faster printing over our current system, which leads to about a 75% reduction in the end part cost. This is the kind of reduction that's needed to really break down the barriers and drive metal additive manufacturing to a true serial production solution. So we're really excited to have the opportunity to present this today, especially at formnext. One of the most important aspects of the Sapphire XC is that it's building on the Sapphire Core. And I really wanted to emphasize this because it's tremendously important, especially as people are going to production with these systems. If you're not familiar with the standard Sapphire is a system, a laser powder bed fusion system that's designed for the production of medium-sized parts. The build volume for our Sapphire is a 315 millimeter diameter and a 400 millimeter Z height. It's dual 1 kilowatt lasers, and it always has been dual 1 kilowatt lasers. And I say that because it's really important that we emphasize that this core is what is driving the Sapphire XC. The Sapphire technology that's really enabled us to emphasize the better parts is what you see on the bottom here. So we have our support-free processes where we've demonstrated the ability to print low angle overhanging surfaces down to essentially 0 degrees without supports. We have our non-contact recoder, which is kind of a critical bit of kit that allows us to do some of the things that we're able to do with the system. And then we have some proprietary solutions around the inert gas flow, our optical train, and particularly our metrology suite that allows for some of the most advanced and complete reporting of the process as it's occurring, of the calibration of the system, kind of a complete quality assurance package that lets users be confident in the quality of the end part. Going back to the dual 1 kilowatt lasers, I think that this is really important to mention because there are a lot of times when scaling up a system means also scaling, for instance, the laser power. And when we are building the Sapphire XC system, all that we're doing is changing the build volume so that we can build bigger parts and increasing the number of lasers. So we're not changing the type of laser. And I'll get to why that's important in a second. So as I mentioned, we have the 600 millimeter diameter, a 550 millimeter Z height. So this is a round build volume, just like our standard Sapphire system. And the thing that we're doing here that's really driving the throughput up is that we've gone from a dual laser system to an 8 laser system. So this is very much leveraging the 1 kilowatt technology that we're using on the Sapphire, but expanding that to 8 lasers. I was watching another product launch this morning, and they were talking about some of the processes that they use in in printing parts of certain materials. And I think one of the things that struck me was that they basically said, you know, for a lot of the nickel-based alloys, we've been printing, and the maximum power we've been using is something like 400 watts. And as you scale that to a full kilowatt, there's a lot of learning that has to go on and a lot of requalification, retesting. If you're printing parts that are certified or qualified, you're going to have to go through a pretty reasonable amount of pain to be able to deliver parts from a new production solution if you've also scaled the laser power by a factor of 2 or 2.5. So one of the critical aspects of what we're doing is that we're not scaling the laser power. This is the same optical train that we're using on our standard Sapphire system, which means that the Sapphire, the standard Sapphire, is a very good way of starting production, of doing low rate production and development. And then when you want to go to full scale production, the Sapphire XC is a solution that allows for an immediate transition to production. And this is with a very minor delta qualification required because the process is the same. We're literally taking the technology that we're using and the optical system that we're using in the Sapphire and scaling it. So again, the Sapphire technology that you see on the bottom is built into the Sapphire XC, and we're able to leverage all of the development that's been done, all the process parameter development, qualification, material certification that's been done on the Sapphire directly to the XC. When you look at the dynamics of cost in 3D printing, it's really important to realize that the printer is really the main driver of part cost, especially with current technology. So as we scale the system, it's really important to be able to scale the printer throughput much more quickly than you scale the cost of the system. And really, this is what you see in the Sapphire XC, right? So we're able to increase the throughput by a factor of 5 while only increasing the cost by a very nominal amount. The more lasers enable a much higher throughput, but there's also some things that have to be considered as you go to multi-laser, as you go to higher number of multi-laser systems, I should say. So as an example, soot is something that you really need to be careful of and how you're doing laser scheduling in order to maintain good material quality as you're printing with this number of lasers. And also laser alignment. I think this is a critical aspect of multi-laser systems that is not an easy thing to address, but something that we've been able to address with the Sapphire through our in-process metrology. So again, we actually have the ability to check the laser alignment every single layer and maintain that through the entire build. The larger printer also enables us to have a much bigger print area. And as long as we're increasing the throughput faster than we're increasing the printer hardware costs, we can drive down that final printed part cost pretty significantly. So we wanted to go through a few examples just to demonstrate the value of the Sapphire XC, particularly to an end user. We have worked with quite a few rocket companies. It's one of the areas where we've had some of our biggest success here in the US. Both small and large rocket companies, from people who are printing just, the turbo machinery, all the way to people who are printing the full combustion chamber and nozzle, as well as their pump hardware and other parts of the engine. And the rocket nozzles are a pretty important demonstration of some of these throughput gains that can be realized with the XC. So if you see here on the left, we have a combustion chamber and nozzle as printed on our standard Sapphire system today. This is a part that's roughly 250 millimeters in diameter at the bell of the nozzle, and you can fit about one of these per build. When you go and look at what you can do on the Sapphire XC, you increase that pretty dramatically. We can fit 7 of these in a single build with the same orientation, the same layout. So we can almost print an entire rocket's worth of engines at a time, depending on the size of your launch vehicle. In terms of throughput time and cost, this leads to some pretty remarkable savings. So as an example, if you had the print of 7 engines on our standard Sapphire system, that would take 1,000 hours. We're able to reduce that pretty dramatically. One of the things that we've also done in the past several months is release our Sapphire Gen 2. So this is an improvement over the current Sapphire system, or I should say over the legacy Sapphire system, that really dramatically reduces the build time by addressing some of the overheads that we had in our original system. So that's a pretty dramatic decrease in the total printed time, but it's nothing when you look at what it is compared to the Sapphire XC. So the Sapphire XC, for the same 7 engine print, would have an 88% reduction in total build time. And what that means in terms of cost is that you go from a manufacturing cost of these 7 engines of something like $100,000 down to a fifth of that, right? $20,000 for 7 engines. And if you're dividing that by the 7 engines, then the part cost, the individual part cost, becomes pretty amazingly low. And I just want to point out here that these numbers are for printing 7 of these nozzles on each one of the systems. So we have the asterisk on the bottom. This is the same number of parts produced on all 3 systems. And that's the same also for our next few examples, where we're again talking about real customer parts and the implication for production of those parts. On the top, you have an example from CR Turbines, which is one of our partners who is producing microturbines for UAV power generation and distributed power generation applications. On the standard Sapphire system, you can fit 4 of these parts. On the XC system, you can fit 17 of these parts, a dramatic scaling of the number of parts that you can print. Mohawk Innovative Technology is a company that we're working with quite a bit on some novel power generation applications. So this is a Department of Energy project, some open impellers, some compressor wheels, where on the standard Sapphire system, you can print 19 of these parts. The 600 millimeter diameter allows you to print 66 of these parts at a time. So again, a huge increase in the production throughput. And then if you look at the total part build time and the total part cost, you see a similar trend to what we were showing with the rocket nozzle, which is for the XC, you have a 77% reduced build time. So that's about a fifth of the build time for the CR Turbines microturbine. And again, for those same 17 parts, the total print cost is $38,000, a remarkable reduction in part cost. So what we're offering as a company now in terms of our build portfolio is the standard Sapphire system, which is, as I mentioned, a great system for medium-sized part production and for kind of the low-rate initial production as you scale towards needing a Sapphire XC. We also have the Sapphire 1MZ. So if you're not familiar with our product offering, this is a system that is essentially the same as the standard Sapphire, but with an elongated elevator. The system's able to build parts that are a full meter tall. So it's the same 315 millimeter diameter dual 1 kilowatt laser system, but with a full meter build height. So we've seen some pretty interesting applications there in oil and gas as an example, some downhole tools. Also, rocket engines are another place where they're leveraging that quite a bit. And then at the end of next year, the first Sapphire XC deliveries will be made. So that is the system that we've been talking about today that really starts to open up some of these additional applications. One of the other things that we're really focused on, and this is again going back to the build it better approach to metal additive, is really delivering the highest customer value possible. So we consider a lot of the metrology, a lot of the sensing, a lot of the kind of subsystems as critical to the product that we're offering. And that means that we don't ship these systems without having, our full sensor suite, without having all of the optical metrology, the calibration, the powder reuse, build reporting. Those are all critical aspects to actually delivering these high quality parts at the end of the day. So we just wanted to highlight a little bit of the difference between what we're offering and what you might find from other laser powder bed fusion manufacturers. So on the optics system, I talked a little bit about the in situ overlay correction. This is the alignment between the lasers as you're printing the part. Absolutely critical as you get into a multi-laser system, something with 8 lasers or even more, that you check the laser alignment constantly. Otherwise, you'll start to end up with seams on your part, and really you're not going to be able to make a single part with all of those lasers effectively. When we look at the thermal lensing, which is our beam stability, our distortion mapping, which is the kind of Cartesian mapping of our galvo systems, we're able to calibrate the spot size inside the machine without any external equipment. And these are all critical to being able to deliver that in-part quality. So really, I just want to emphasize here that while additive has really focused on the build it faster approach, Velo3D has also been very successful in delivering on the promise of better parts. And now with the launch of Sapphire XC, we are able to also pull in the cheaper aspect. So where it used to be faster, better, cheaper, pick 2, now I think you can have all 3. With that, I'd be happy to answer any questions.
Thank you, Zach. Real quick, we're going to open it up for a couple questions. I think we have a few minutes here. Please submit your questions through the Q&A button on the bottom if you want to do the question session. This is a live session, so we will try and get to your questions. So Zach, one of the questions that I'm seeing here is you mentioned Sapphire and Sapphire Gen 2, and maybe you could talk about the differences between the two there in one of your graphs.
Yeah, absolutely. Let me see if I can get back to it. So I think I kind of emphasized this a little bit, but when we had originally built Sapphire, the goal wasn't to print fast necessarily. The goal was to print the best parts possible to deliver kind of the industry first support-free and low-angle processing without requiring supports, and then to do that all with the metrology backing up the quality of the printed parts. So that I think was a really great first step, and it demonstrated kind of the technology and the ability to do these things. But in the past year, we've really been focused on helping to drive the throughput of our current Sapphire system so that it's more cost effective. And that's what Sapphire Gen 2 represents. This is a refinement of the Sapphire system that allows us to not only melt material much more quickly, but also reduces some of the overheads associated with, for instance, metrology and recoding and other aspects of kind of the operation of the system in a way that has a pretty dramatic effect on the total printed part time.
A couple questions here about large parts. Are there any stitching issues experienced for large parts, and how does Velo address the overlay of lasers?
Yeah, so I think stitching issues are something that everybody should be aware of and should be looking out for when you're printing a large part with a multi-laser system. One of the things that Velo's been able to demonstrate pretty effectively is the ability of our in situ metrology to maintain laser alignment of the lasers to each other in order to eliminate stitching lines. And you may have seen this in the past on some of our parts if you've been by our booths at a trade show or in some of our videos. But when we print parts, there's no visible stitch line. And the reason for that is that we're able to initially, before a print during our calibration, align the lasers to within something like 20 microns, laser to laser, and then to check that every single layer, if that's what you require, in order to print these tall parts. If you think about the 1 meter Z system, so this is a full meter print that can take, that's something like 20,000 layers if you're printing at a 50 micron layer thickness. So for 20,000 layers, you need to maintain that 20 micron fidelity. And doing that while temperatures are changing, while other things may be varying, it can be very difficult if you don't have that metrology built in. So that's one of the reasons that Velo is very confident about the 8 laser system and the ability to maintain overlay. We've been able to successfully demonstrate that so far and are scaling that now to the 8 laser system.
Another question about the lasers. Are the lasers full field or do they have dedicated zones?
They're not quite full field. And the reason for that is that the process depends on the angle of incidence of the laser at the build plane. So in order to maintain high part quality, especially as you get to some of these more aggressive processing conditions, such as printing 0-degree overhangs without supports, it is beneficial to be closer to the laser normal. So we try to keep the lasers in kind of a zone, a circular zone that's a certain angle of incidence away from the laser normal, such that we can ensure the process is meeting the highest quality standards.
Are there any ITAR regulations on the technology?
The technology itself is not an export controlled technology. I think there are some limitations around end use applications. So, the US government doesn't like to export things that are being used to make launch vehicles for nuclear weapons, which seems like a reasonable request. But no, the technology itself is not a export controlled technology.
And you mentioned the melt pool monitoring system, I believe. Is that offered or is it planned? And how's the data used? Is it included in the build report?
Yeah, absolutely. It is offered and included with every system. So it's not an option. It's not an add-on. It is part of the base system. We consider it core to the functionality of the machine. And if you're printing parts on a system, we think that you need to know the quality of the part regardless. So it's included with the system. The data is included with Assure quality software, which is also part of the system offering. And the comprehensive build reporting leverages that to not only give you insight into how the part was made, but we have now defect detection that is also highlighted. And I think in early December, we'll have a full webinar on defect detection and the things that we're doing around that should have some pretty surprising, I think, implications on part quality. We're really excited to announce that as well.
One of the selling points of Velo 3D is the reduced need for support structures. Can you elaborate on how we achieve that?
Yeah. So reducing the need for support structures is really not as sexy of a process as you might think it should be. It's really about process control. And Velo as a company has been a very process control oriented technology company since its inception. Our background is semiconductor capital equipment and doing process control and development as it relates to these semiconductor processes. So we've leveraged a lot of that kind of rigor and approach into developing the processes that we have running on our Sapphire systems. So, when people say that they've, in the past not been able to print certain alloys at a full kilowatt, we've been printing all of our alloys at a full kilowatt for several years. And part of that is due to the rigor that we have in our process development team. That really is kind of the core of what we're doing as a company, is the process. Everything else that we build as a product is to support that.
Here's a question that since the machines are getting so fast, is the setup process automated, or does the operator have to start the machine and then control the first layers? How do we approach that?
Yeah, that's a good question. So as you drive the processing faster and faster, you have some interesting dynamics that happen as it relates to kind of variable costs, right? So the material starts to become a much more important aspect of the printed part cost. And as referenced in the question, the setup can also be an important part of that. So the setup is not automated. It still requires loading a build plate and then starting the system. But one thing that's actually a pretty interesting difference between our system and a lot of our competitors is that you don't need to monitor the first several layers. Because our recoder doesn't actually touch the powder bed where you're printing, getting a build started and doing kind of the initial like leveling type of operations that a lot of people do when they're trying to set a recoder blade is not required for our machine. So starting a build can be much faster and much less touch intensive.
And since you mentioned the recoder, there's a question, what is the non-contact recoder?
Yeah, it's a fairly popular question that we get quite a bit. The non-contact recoder is a way of laying down powder for every layer and doing so in a way that doesn't touch the plane where you're melting metal. And that's really important because as you build these very low angle parts, they tend to stick up through the powder bed. And if you have like a hard recoder or even a kind of a flexible polymeric recoder, you contact a part and that is problematic, we'll say. It leads to build crashes. Our recoder essentially lays down a layer of powder, then removes a certain amount of that powder as it's passing to end up with a 50 micron layer. And we're happy to go into more detail on that. If you have specific questions about it, definitely let us know and we can talk in a more intimate setting.
Okay, just kind of doing a time check here. We're kind of up on the half an hour. So the last question, how can people get in touch with you if they want to learn more about the Sapphire XC?
Yeah, absolutely. So please don't hesitate to reach out to our email address, info@velo3d.com. If you want to reach out to me personally, my email is zach@velo3d.com, Z-A-C-H. Happy to try to answer as many questions as we can and really get the word out about this technology and the implications that it has for serial production.